Right, thank you very much for having me here. So the story I wanted to tell you about today is from this paper earlier this year, and it's about finite temperature quantum topological order in 3 dimensions, and it's together with this set of people. In particular, Tyler Allison has did a lot of the heavy lifting. And okay, so this is the last talk of the day. Probably everyone is a bit tired, so let me just start by telling you the punchline, so you can then fall asleep if you want. So the result is that you're an example of a system in 3 spatial dimensions that exhibits quantum topological order at finite non-zero temperature. And what I mean by quantum topological order is some sort of synonymous with long-range entanglement. And I will define this in a few slides. But what I basically mean is that it's a state that you cannot get by taking the classical mixture of pure states, which you can get from a product state by some local operations. So it's something that has sort of quantum entanglement that is long distance and is genuinely quantum. And all previously known examples that exhibited this at finite temperature require you to go to dimensions at least 4. So to our knowledge, this is the first example where this happens in 3D, which is good because actual materials are in 3D, so it's nice. There's a caveat, which is that a lot of these examples which have this property in, for example, 4D, also have another nice property, which is that you can use them as a passive quantum memory that stores quantum information. So our example does not have that property. It's not a passive quantum memory. And the sort of key ingredient that allows all of this to happen, that is different from other examples, is that it's a system in 3D which has some emergent fermionic excitations. So even though your underlying degrees of freedom are spins, which are bosonic, your emergent excitations are fermions. And this is what gives you this sort of non-trivial entanglement. Okay, so to tell you how this works, let me just first sort of set the stage and introduce some language that I will use by reminding you of some facts about the 2D version of topological order at 0 temperature in the toric code. So I have the toric code, I have 2 types of terms, vertices and plaquettes, which are product of X and product of Z, qubits living on the edges. And one way of describing this, which is kind of the more modern language, is that it's a system which has so-called one-form symmetries. If I take some closed loop of Z's or closed loop of X's on the dual lattice, this commutes with the Hamiltonian. And these 2 symmetries, the kind of X and Z loops, they have an interesting property called an anomaly, which is that they locally anti-commute. If I have one of these red loops and the blue loops intersecting at one point, then there's a -1 when you try to commute them to each other. And one way of saying this is that the objects charged under one of these symmetries are exactly the generators of the other symmetries. So there's interesting kind of dual relationship between your 2 symmetries. And this is just another way of saying something that you knew about the toric code, which is that the anyon excitations, which is what you get if you open up the loops to get some open string, have a non-trivial braiding. This anomaly is just another way of saying sort of the same fact. And another property about the toric code is that if I put it on a torus, there is a degenerate ground state, and the operators that take you between the different ground states are these non-contractible versions of the same loops, which is one way of seeing that this higher form symmetry in this case is spontaneously broken. The symmetry has some non-trivial action on the ground states. And the physical picture behind that is that your ground state is some soup of these loops, which are the charged objects, so they're kind of condensed and everywhere. Okay? And there's another property which is important for my talk, which follows from all of this, which is the long-range entanglement of the ground state, meaning that you cannot approximate the toric code ground states as any short-range entangled state, meaning any state that you can prepare from a product state with some low-depth local quantum circuit. And there's a particularly sort of crisp, strong version of this statement from this relatively recent paper, which says that the overlap with any state that you can prepare with a depth D circuit is exponentially small in the ratio of the linear system size L and the depth of the circuit. So you really need to make the depth order L to have any appreciable overlap with the ground state. And the intuition behind that can be seen as follows, that imagine that I'm acting with some open string on my ground state. And because I have this symmetry under the closed loops, it means that I can move this string around. As long as the endpoints remain at the same place, I could write down a bunch of different strings, which all must have the same effect on the ground state. And it turns out that if you assumed that the state was also short-range entangled, prepared by a depth circuit, then it would imply that I could replace this string with a product of two operators acting only near the endpoints, with some size that kind of is proportional to the depth of the circuit. And this is clearly inconsistent with this non-trivial braiding, because if I now try to braid something around one of the endpoints, if it can be created locally, there is no way for this braiding to sort of pick up the fact that I created something. So that's why you get an inconsistency, and the state must actually be long-range entangled. So what happens if I go from 0 to finite temperature? Because unfortunately, actual materials always exist at some non-zero temperature. So we'd like all of this to be true at finite temperatures. But in 2 dimensions, it's not. What happens is that any finite temperature, these point-like anion excitations, they proliferate. You get them everywhere, and that destroys this non-trivial topological state. And the way to see that is like a simple entropic argument that tells you that the energy cost of one of these excitations is order 1, but you can put them anywhere in the system, which gives you a logarithmic entropy, so the entropy always wins. And then in finite temperature, these things pop up all over the place. And the problem with that is that if I now try to look at what happens when I apply one of these symmetry operators, these closed loops, the phase I pick up, previous state was always +1, but now it's either plus or -1, depending how many of the other type of anyons I'm going around, and that number is just fluctuating all over the place, so I get lots of different contributions that cancel, so I get something that's basically 0. Of course, given the theme of this conference, I'm obliged to mention that you could stabilize this 2D toric code by using active error correction. But that requires you to maintain some sort of strongly non-equilibrium state that requires some resources. It would be really nice to have something like this, just in equilibrium, put your system in the fridge, cool it down, and get some topological order. And this picture sort of suggests how you might do that. The reason this 2D toric code was unstable is kind of the same reason why one-dimensional systems tend to be unstable at finite temperature. For example, if you have a 1D Ising chain, at finite temperature, domain walls proliferate all over the place. And there, the way to make it stable is to go to higher dimensions, go to 2D or 3D, suddenly the Ising model becomes stable. And something like that happens here as well, but I have to go all the way to 4 dimensions. If I go to 4 dimensions, there is a version of the toric code where both type of excitations, E and M, both become extended loop-like objects. And that extended loop-like object now can survive at finite temperature. It doesn't have to immediately proliferate the same way as point-like excitations do. And there are various consequences of this. So this 4D toric code has a non-trivial phase at low temperatures, which first of all works as a passive quantum memory. So this ground state degeneracy that I mentioned in the 2D toric code now in this 4D version exists also at low temperatures above 0, and you can use that to encode some quantum information, and the system just preserves that. It's sort of like a magnetic hard drive that just passively preserves some memory, but now you can do this for quantum memories. And another consequence is that you have this kind of long-range entanglement. And one question is, how do you even define that at finite temperature? So the definition I'm going to use is this one, that I will say that a mixed state has long-range entanglement if I cannot write it as a mixture of pure states which are short-range entangled, in the sense that I can prepare them as a low-depth circuit. So this is very nice, but it's in 4 dimensions. So the question is, what about 3D? Can you do something in 3D that has some of these features at least? So it's useful to think about just the 3D version of the toric code first. This will not quite work, but it will build some intuition. So I have a 3D model, qubits living on the edges of a cubic lattice, and I have similar terms as in 2D. There's a vertex term now acting on 6 qubits around the vertex, and there's 3 different types of plaquette terms on the 3 differently oriented plaquettes. And This is a product of x, this is a product of z. People paying attention will notice that I switch colors compared to 2D. Don't get confused by that. And so what happens is that, again, have two types of symmetries, but now they're a bit different. So one of the symmetries still corresponds to some loop in this 3D model, a product of z operators along the loop generated by these paquette terms. I'll refer to this as an E loop. But the other symmetry now doesn't act on loops, it acts on surfaces. If I multiply these vertex terms together in some volume, I get some product of axes on the boundary. So it's a different symmetry now acting on the surface. But there's still a notion of these two things sort of locally anti-commuting. When an E loop pierces one of these M surfaces, there is an anti-commutation. And that means that there is again a non-trivial braiding, which, or there's still this kind of anomaly between them, and that leads to non-trivial braiding, because now I can think about excitations created by opening up these objects. So I can open up a loop to create two point-like particles at the endpoints, or I can open up an X surface to create a loop-like excitation around the boundary. So there are now two types of excitations. One is a point, the other one is a loop. I can talk about braiding, let's say, a point particle around the loop, and I again pick up a non-trivial phase. There's again a non-trivial braiding. And by a generalization of the previous argument, this implies topological order and long-range entanglement at 0 temperature. But if I go to finite temperature, I kind of face the same issue. One of my particles is point-like, is going to proliferate immediately. And indeed, because of this, one of the two symmetries is kind of goes out the window at any finite temperature because these E particles proliferate. On the other hand, the loops do not proliferate immediately. At low enough temperatures, these loop excitations now exist at finite temperatures, but they remain small. So you can argue for this in a way that's kind of similar to the Pyros argument you have in the Ising model. There is now some competition of energy and entropy, and at low enough temperatures, it leads to a state where the typical size of loops is small. The largest loops you end up seeing in a system is kind of logarithmic in the linear size. It's much smaller than the system size. And it's only at some finite temperature that these loops start proliferating. And one way of saying this is that this E-loop symmetry that I talked about kind of still exists in some emergent way at low temperatures. If I sort of zoom out, coarse-grain the system, I don't really see these tiny loops. It kind of looks like a state with no loops, and that means that I still have a symmetry. And if you find that confusing, I'll get back to this and define this emergent symmetry in a more precise way later. So what this means is that there is a non-trivial phase at low temperatures below some Tc, but because one of the symmetries is gone, and I really needed this anomaly between the two different symmetries to get this quantum topological order and a quantum memory, here, this low temperature phase I get is actually a classical state. It only works as a classical memory. And another consequence is that it also doesn't have long-range entanglement. And there's a nice argument due to Hastings for showing why it doesn't have long-range entanglement. So what he pointed out is that for a stabilizer Hamiltonian, if you look at the finite temperature state, you can always rewrite it as a classical mixture of the ground states of a family of slightly deformed Hamiltonians, where you drop some of the terms from your Hamiltonian. So each term in the Hamiltonian I either keep or I drop. I look at all of those different Hamiltonians, look at their ground states, and I take some mixture of all of those. And what you can see is that this mixture is dominated by cases where you drop many terms. You can think of this dropping of terms as sort of punching a hole in the system, and the relevant contributions are those where these holes are kind of log L apart. They are pretty close. And now this gives you a way of disentangling the state. Basically, in each of this log L sized patch, you can use this hole that you created to kind of start disentangling there and kind of successively disentangle the state. And you only have to go to this log L distance. And what this means is that the state is trivial. And the question is, now, can we somehow avoid this? In this bosonic toric code I told you about, the state ends up being trivial at any finite temperature. Can we somehow avoid this without going to higher dimensions? And the intuition of how to get around this is the following. The physical picture of this disentangling procedure is that what you do is that you use these holes to condense some of your anyons. You can sort of create a condensate of the anyons and sort of grow that to eat up the whole system and make it trivial. And condensing something only works if it's a boson. So what if I had a version of the system where my emergent excitation was not a boson, but say a fermion, then I cannot apply this argument and might actually have long-range entanglement. So this is where the fermionic toric code enters the picture, which is a slight modification of the system I had before. Qubits still live on the edges, the vertex term is still the same, but I modified the plaquette term slightly so that it's no longer just this product of z's along a plaquette, but it has this kind of little protrusions of two X operators for each plaquette. It's like a slightly weird looking version of the toric code, but it's still pretty simple and it's still a stabilizer model. All these terms commute with each other. And we can look at the symmetries again. So one of the symmetries is the same. The surface generated by the vertex terms is the same. But now the loop looks a bit different. So if I look at this loop, again, now it has this sort of dressing with a bunch of X operators going around it. And I will refer to this as an F loop for a reason that will become clear in a moment. And the point is that you can show is that now not only do you have this sort of mixed anomaly between the two symmetries, but just this loop symmetry by itself has kind of a self-anomaly. So what does that mean? What does that mean physically? To really see it, it's worth again looking at the excitations created by these symmetries. And the main point is that now if I open up the loop and look at the excitations created by it, it turns out that these are no longer bosons, but fermions. Meaning that if I take two of them and exchange them, I get a minus sign. So this is an example of this kind of emergent fermion, even though the underlying microscopic degrees of freedom are bosonic or spins, and this is a manifestation of this anomaly. And this means that this Hastings argument for why the system must be trivial doesn't apply anymore. And indeed, what we prove is that, in fact, at low enough temperatures, the finite temperature state of this model is actually non-trivial. It has long-range entanglement. So the statement is the following, that if I look at the fidelity between the finite temperature Gibbs state and any short-range entangled mixed state, this fidelity goes to zero faster than any polynomial in the system size at sufficiently low temperatures. Okay, so here is an outline of the proof of this statement. So the idea is that I start with my state at low temperatures, and again, as I was telling you before, this is a state where the loop excitations remain small. They're kind of only logarithmic in the size of the system. And that means that I can use some local process to clean up all of these loops and end up in a different state which has no loops at all. And then for this state, we can use a generalization of this argument I mentioned before to argue that because the existence of the emergent fermions in the state means that you cannot approximate it as something short-range entangled. And the important step is that because the way you went from the initial state to this new state is local, that means that if this cleaned up state is not short-range entangled, then your initial state must also not have been short-range entangled. So here is a slightly more detailed version of the same argument. So to make this argument work for mixed states, you have to sort of think a little bit about what is even the symmetry for mixed states and what does it mean. And in particular, to get these arguments to work is you need something called a strong symmetry, meaning that you need a mixed state rho which is invariant under multiplying with the symmetry operator, which in this case is this loop associated to the fermions only from one side, not conjugating from both sides, but just multiplying from one side. This is called a strong symmetry. And you can think of it as saying that not only is rho as a mixed state itself invariant, but it's kind of made up entirely by pure states that have the symmetry. And that's why you can kind of generalize arguments from pure states to mixed states if you assume this. And indeed, you can use the same sort of argument, the contradiction of the state being short-range entangled, to show that if this symmetry has an anomaly, in particular if the endpoints behave as fermions, then the fidelity with any short-range entangled state must be exponentially small, once again in the ratio of the system size to the sort of circuit depth that you try to use to approximate it. So this is all good, but if I look at the finite temperature state, that does not actually have this strong symmetry property. And the reason it doesn't have it is because you have these loop excitations, which have a non-trivial braiding with my symmetry loop. So if I apply the symmetry loop, I have a bunch of these short loops in the system. Each one gives you a -1 sign. So you again get lots of contributions with different signs, and you get something sort of non-deterministic that doesn't satisfy this condition. So this is where this cleaning out idea comes in, that instead of applying the symmetry to my original state, I can apply some cleaning procedure, some local quantum channel to turn it into a different state which has the symmetry. So the idea to go from this state with a bunch of short loops to a state with no loops at all. And the way to do this is the following. So the colors in this picture might be a bit misleading. These are all the same types of loops. So blue and red no longer means X and Z. It's just supposed to tell you which loops you get rid of in each step of this procedure. So the procedure goes through 4 steps. I start with my initial state, which has some distribution of loops. And I divide the system into a bunch of patches. And I can apply some channel on each patch individually to get rid of the loops entirely inside that patch. And now I just repeat this for 4 shifted versions of this patch decomposition. Like I shift my patches like this, then finally like this, to kind of cover everything. And at the end of this, I end up with a state which still has some loops, but only those loops which are bigger than the size of the patches. Everything that's smaller, I cleaned up. And so the point is that if I make the patches big enough, bigger than the typical size of loops I see, the resulting state will be very close to a state that has no loops at all. In particular, the error you make is something that goes like the volume of the system times something that's exponentially small in the size of the patches. And now, for example, if you make the size of the patches go as something like the square of log the system size, then it's big enough that this error is smaller than any polynomial in the system size. And at this point, you're basically done by using like a triangle inequality, so combined with the data processing inequality. So I look at the fidelity between my Gibbs state and the short-range entangled state. This is upper bounded by what I get if I apply this cleaning up channel to both sides. And on the one side, I get something that's now close to a state without loops, which must therefore be far from any short-range entangled state. And on the other side, I get something that's still a short-range entangled state. Because due to the fact that this cleaning up is local, this means that if I apply the cleaning to any short-range entangled state, what I get is still short-range entangled. It's something that I can create with, like, let's say, a logarithmic or log L squared circuit. And now, just using the fact that basically combining these two inequalities, I get this result, that from a triangle inequality, that the fidelity to any short-range entangled state is the sum of these two things, both of which are kind of very small, decreasing faster than any polynomial in system size. Okay, so I end up with this phase diagram that once again there is a TC, there is a phase transition at some finite temperature, which happens when these loops get big and start proliferating all over the system. And the state below TC is still only a classical memory. due to the fact that my point-like excitations have proliferated immediately as soon as I went to finite temperature. So this finite temperature state is still distinct from the zero temperature state. It's a different phase of matter, but due to the argument I just gave, it still has long-range entanglement. So that's kind of maybe one interesting feature to point out, is that this is kind of a phase that only exists as a mixed state. It doesn't exist as a pure state. So in equilibrium, this is a phase that only exists at finite temperature, not at zero temperature, even though it's also quantum in some well-defined way. Okay, so you've already seen this slide. Let me just close with mentioning a few sort of open problems. One is that this is kind of an abstract proof that this state has long-range entanglement, but it would be nice to have some actual diagnostics, something that you could calculate or measure that would actually tell apart whether you are in this phase or not, which we don't have yet. And the other, even more interesting question is, so the whole point of going through this exercise of having this 3D system was that this is something that might actually exist in a material that you could prepare in a lab, so of course you could try to prepare more complicated things in like a cold atom experiment, but this might actually exist in like a condensed matter system. So it would be very interesting to find any system that might actually realize this. Yeah, so those are kind of interesting open questions to think about. And yeah, thank you for your attention.
Thank you, Tibor, for the great talk. Questions?
Maybe I've already mentioned, but is there an estimate on the lifetime of the, how long, is the lifetime scaling with e to the L or e to log square L, or, what is it? Yeah, do you know what the lifetime is?
Of the classical memory that you have at low temperatures. So it's exactly the same, I think, as it would be for just like the vanilla 3D toric code, and it should be exponential in L, I think. It's basically like to sort of destroy the memory, you have to like nucleate a large loop proportional to system size, and I think that's suppressed by something that's like e to the minus L.
I guess in your proof of no short-range entanglement, there's something like e to a log square L coming up, so that's not related.
That's not the memory time. That just has to do with like the typical size of loops at finite temperature.
So another thing is that this short-range entanglement, like this fatality bound, it seems to remind me of this NLTS, but I realize, I guess, in constant dimension, you don't really get this LTS, so could you, but then I guess you're saying that skip states are very entangled, but then there's actually lots of low-energy states that are not very entangled. And how could you comment on that?
Yeah, so that's true, that like NLTS is a much stronger statement, because then you require that there's no low-energy trivial states. Here you just require that the Gibbs state itself is non-trivial, or basically that. And that's much easier to get. That you can get in finite dimensions. But yeah, you could definitely write down some states at low energies which have low entanglement. It's kind of an interesting question, the relationship between this and Sun-Won's talk earlier today. That like, what does this imply about thermalization? So this is exactly an example that violates the condition that he had, that the thing that you get by naively decomposing the Gibbs state is not, or you cannot decompose the Gibbs state into short-range entangled things. But you could have some short-range entangled things at the same energy density. So what happens to those if you evolve is not obvious. Yeah, so this is commuting projector. So this doesn't thermalize, but you could perturb it slightly to make it non-commuting projector. It would probably be still in the same phase with the same long-range entanglement.
So you said that this like finite temperature phase is like different to the zero temperature phase. I see that like in this model. Do you know that that's true? Like even if you like start perturbing the Hamiltonian, there's no way to get like a zero temperature phase with this topological order.
Yeah. So all of this sort of comes off of some recent work on just sort of classifying states, where you can define an equivalence relation between mixed states, and think about equivalence classes. And the statement is that basically the state that we have here is provably not equivalent up to like finite depth quantum channels to any pure state.
So maybe like in terms of the diagnostics, like very naively, is this overlap, like the maximal overlap with the generic product state or like short-range entangled state already like a way to identify, or like are you also looking for like measuring like the fermion statistics or?
Yeah, I mean, yeah, I mean, the maximal overlap with the product state or a short-range entangled state, in some sense, yes, that would be a kind of order parameter maybe, but that's very non-feasible because it involves this optimization over like all states. So what you would really like something that you can at least just sort of, given a state, compute. So I mean, what we believe is that there's probably a way of detecting this in something like entanglement negativity, but I guess we haven't proved that.
Yeah, but like if you just randomly sample over like a finite set of product state, would that be a sufficient measure or not really?
Yeah, I mean, maybe. I'm not sure. I would expect that you would see, maybe you would see something, but I don't know if it's like really sharply distinguishing phases.
Two related questions. Is using a fermionic Wilson loop tricky because you're at finite temperature? And the second is if there's no zero temperature analog, then how do you think about stability? Like without a gap and things like that. Yeah.
Yeah, I mean, I think the sort of, I mean, how do you think about stability, I think applies even if there is a zero temperature version, like, you know, stability at finite temperature doesn't obviously follow from stability at zero temperature. I think what you want to argue for stability is still just that these loops you have, they remain small, even if you slightly perturb the Hamiltonian, that they don't immediately proliferate. And I think you should be able to argue that in the same way as you would argue for other, like the usual 3D or 4D toric code. Sorry, what was the first question?
Challenges with using this dressed operator that you had, which was like a fermionic string operator, using that as a diagnostic.
Yeah, I mean, I guess one challenge is the way I defined the emergent fermionic operator. It required pushing everything through this quantum channel. So it's not, because that doesn't necessarily give you something unitary that you would know how to apply. Although I guess there might be caveats to this statement. I think it's more that, not the fermionic nature. Like, you know, in the original model, the loop operator is some perfectly fine product of Pauli's. It's more like how to do this smearing out at finite temperature. But yeah, that would be like one way of getting an order parameter.
Could you expand on the comment that the low temperature state is not in the same phase as the ground state? I think I missed what the argument was there.
Well, so you definitely have kind of a lower degeneracy that, like, in the ground state, you have this sort of, it's kind of like a quantum memory in the sense that you have anti-commuting operators acting on the ground state, similar to like the 2D toric code ground state. At finite temperature, this is only a classical memory, so you kind of only have the diagonal part of that. And you can also show that it's a distinct phase in the sense that you can define an equivalence relation between mixed states. Like you say, two states are equivalent if you can go both ways between them by a finite depth quantum channel. And this is not equivalent to any pure state.
So is the point that you can't like clean up the point excitation?
Yeah, exactly. You can't really go back quickly to a state without the point-like excitations.
More questions?
So like, what happens if you just contract them? Like, just contract them at closest phase?
Yeah. I mean, I would think that you would still. I mean, one thing that's definitely true is that you have like a problem of like sort of decoding back, like, you know, if I start in like a specific ground state, heat it up, and then try to cool back, I can't really decode back to the state I started from. Like I might end up in some ground state, but not as the one I started from.
Isn't that saying that there are some ground states which are in the same phase as the like finite temperature memory and vice versa?
I think probably it's like the things that are in the same phase are still mixed. It's like some particular mixture of the ground states. Like basically erasing part of the information in the ground state is the thing that's in the same phase of the finite temperature, I think.
All right, let's thank Tibor again. See you all tomorrow.